Hello, everyone. Welcome to PSY 601 online lecture 8. So let me go through the reading stuff and the homework, and then I'll tell you what we're going to be talking about today. So I'm having you, just like last time, I had you read ahead to the repeated measures and Friedman, which will be a big part of our conversation today. This time I'm having you read ahead to the correlations, Pearson correlation, Spearman correlation, point by serial correlation, and then into linear regression. So take a look at those. I'm sure we'll go through them together as we go through the next piece, but do take a look at them. I think it's helpful. For your homework assignment, I do believe that this time we'll do chapter 9, 9.2, and 9.8, A and B as usual. If something changes with that, I will let you know. Please also understand that we're still going to keep the assignments on Wednesdays. That's my plan anyway. I think that's the best way to do that after we've had a chance together to discuss through the material. So I'm giving this to you ahead of time, but we can talk through the assignment more, and I will get it to you for Wednesday after class. Okay. So today what we're going to talk about, like I said, we're going to spend a lot of time on repeated measures ANOVA and the Friedman test. Okay. Then we're going to get into all different other kinds of ANOVA that exist. We're not going to actually go through how to do these in SPSS. I would like for you to understand the differences between these different ANOVAs and where you might use them. So that's how we're going to approach that. Okay. So repeated measures ANOVA. So the one-way repeated measures ANOVA is an extension of the paired samples t-test or dependent samples t-test. It's used to determine whether there are any statistically significant differences between the means of 3 or more levels of a within subjects factor. Okay, so in other words, we have the same participants that are tested 3 times. Okay. And that's what we say in the next sentence. The levels are related because they contain the same cases or the same participants at each level. Okay, so it could be that they're tested 3 times under different conditions, or tested 3 times and we're interested in the timing of the test. The participants are either the same individuals tested on 3 or more occasions on the same dependent variable, the same individuals tested under 3 or more different conditions, okay, on the same dependent variable. The test is also referred to as a within subjects ANOVA or ANOVA with repeated measures, but I think repeated measures ANOVA is the most common way we refer to this test. Okay. So where might you use this? If there are differences between 3 or more time points, if that's what you're interested in, so you're looking at the same people on 3 different times, and you want to see if there are differences. If there are differences between 3 or more conditions or treatments. Now, again, this is the same participants participating in all different forms of the treatment. So just to give you an example, we'll actually get to one in just a little bit, but just to give you a heads up on an example, what if you put people in a driving simulator on using 3 different methods of phone use, either no phone use, or hands-free phone use, or handheld phone use. And you saw how well they did in the driving simulator under those 3 different conditions. So, but they would be going into that driving simulator 3 times under those 3 conditions. Okay. Also determine if there are differences between 3 or more change scores. And that one is a rare one. I don't think we'll be dealing with that too much. Okay. So how about the one-way ANOVA versus the repeated measures ANOVA? Well, they're calculated quite similarly. However, since the same participants are in each condition, the individual differences or error can be removed from the denominator, from the SS within and the MS within. And that means you have more ability to detect differences due to the IV or factor. So that probably sounds like a bunch of mumbo jumbo. So let me actually show you an example, and I think that will help. So here's the example I was just talking about, performance in a driving simulator. And we have the people who either use no phone, a handheld phone, or a hands-free phone. Okay, so this is a NOVA example, right? And so in this example, we have 1, 2, 3, 4, 5 people in the no phone group, 5 people in the handheld phone group, and 5 people in the hands-free phone group. So 15 people total. Okay. If I ran this through SPSS, this is what I would get. Very nice healthy F of 11.2503, P less than 0.01. And just notice here the within numbers, the 16, the 12, the 1.3333. Okay. Just observe those. Watch how they go down and the F jumps up. These numbers stay the same. The 3215, those will stay pretty much the same. It's this that jumps up and these that jump down. 3215, as I promised, stayed the same. These numbers get a lot smaller. This jumps a lot bigger when I just change it to run as a repeated measures ANOVA. That's the only thing I did. Okay, so here I ran it saying, nope, I have 15 people. Here I ran it saying, nope, I have 5 people who did this 3 times. Okay, so you can see how, again, just using the same data, how we really increase our F, increase our P, decrease our P, decrease our error here, or probability of a type 1 error. So repeated measures, as we said, really reduces that within error. Okay, because we don't have individual differences to worry about. All right. Let's go through the assumptions. First, you have one dependent variable that is measured at the continuous level, interval or ratio. And here are some examples of continuous variables, such as anything with time, honestly, intelligence, measured using an IQ score, exam performance measured from 0 to 100, weight measured in pounds or kilograms, and so forth. And you have one within subjects factor that consists of 3 or more categorical levels, right? It could be pre, middle, post, or it could be no phone, handheld phone, hands-free phone. Could be anything. All right. There should be no significant outliers in any level of the within subjects factor. So that's probably no surprise. We've talked about no significant outliers before. Your dependent variable should be approximately normally distributed for each level of the within subjects factor. Also no surprise. That's getting back to our Shapiro-Wilk that we've been using. This one's new. Known as sphericity. The variances of the differences between all combinations of levels of the within subjects factor must be equal. So the variances of the differences between all combinations of levels of the within subjects factor must be equal. So if that doesn't make a lot of sense to you, that's okay. We're going to continue to talk about sphericity, but basically what we're saying is we're going to have 3 different within subjects levels, such as pre, mid, post. So when we look at all those differences, are the variances of all those differences equal? Okay, all right. Now we're gonna go over to Laird and look at some of the material there. So just so you can see, these are the pages that we're going to look at together, okay? So I certainly invite you to look at them, as I go through them, but also to maybe go back to them later and re-review them for yourself, okay? Or review them for yourself, okay. Okay, so here we are in Laird on page 6 as promised. And let's just briefly talk about the example, what we're going to be looking at throughout the rest of this experience. Okay, so we've got the C-reactive protein that we're seeing if that's going to change from exercise. And we're looking at the 6-month exercise training program. And we're going to look at 3 different points: pre-intervention, midway through the intervention at 3 months, and immediately post-intervention. I'm guessing that would be at the end of 6 months. Okay. So those 3 levels reflect the 3 levels of our within subjects factor that we might call time. Okay, so we're measuring this CRP protein, the CRP at pre, mid, and post. Okay. So when you set up your data, you want to have the scores on the dependent variables separately for each level of your within subjects factor. So I think that's easier looked at than discussed. So here's your variable view in SPSS statistics with CRP pre, CRP mid, CRP post. So you're basically setting them up as 3 different variables. Okay. Oops, sorry. Okay. This is a long to-do about whether you should put your variables in order. I would say to keep your life easy, just think about it beforehand and put them in order. Now, if it's a time thing, that's pretty easy to put in order. If it's a phone thing, like we were talking about before, no phone and hands-free phone and handheld phone, you might want to think through how you expect your results to come out and then order them appropriately. Okay. All right. So we can talk more about it in class, but I'm going to move past that for now. Okay. So here's your data view in SPSS, and you can see here's our people when they had the pre-test, same people with the midway test, and same people with the post-test. And yes, this should be the same person 1 at all 3 time periods, person 2, and etc. Okay. Now, if I was being really fussy, I'd say I'd like an ID number here, but I won't be that fussy. Okay. All right, so we've got our 3 variables. Let's move on. So I know we did already talk about the assumptions a little bit, but let's just remind ourselves about the outliers. Remember, we don't want any significant outliers. We want approximate normality for each level of our within subjects factor, and we don't want violations of sphericity. I will tell you that sphericity is one of those that we're actually going to run right at the same time as we run the repeated measures ANOVA. So we'll come back around to that. But I will tell you, you very often do violate that, and then you just use a slightly different way to interpret it. So it's not bad. But with the box plot that we'll use for the outliers, and with the Shapiro-Wilk that we'll use for the normality, if we do violate those, either one of those, we will most likely be moving over to the Friedman test. That's the alternative to the repeated measures ANOVA. Okay, so let's talk about running the explore procedure like we have in the past. We go to descriptives, we go to explore, and we go ahead and bring over the CRP pre, CRP mid, and CRP post. Then under plots, we can check off the stem and leaf. We do not need that, and we check the normality plot with tests. So I'm kind of hoping this is starting to become a little bit more rote as you do it, but you can always look at these instructions. Then you click on continue, and we hit OK to generate the output. Here is what we get. Right, here is our standard box plots that we're used to looking at. You're determining if your data has outliers. This would be an example of when your data does have outliers, right? And once again, I will remind you that the 4 and 5 don't pertain to the actual value. It pertains to the case number. So this is case number 4. This is case number 5. Okay. All right. Oh, if you had used an ID variable, then I believe these would actually pick up your actual ID variable. So that's kind of cool. All right. So this is the same old thing about how to deal with outliers. And it's certainly worth looking to see if you have any data entry errors, measurement errors, or if it's genuinely unusual values. And then you have to make the decision as to whether we're going to keep the outlier or remove the outlier. If it's a genuine value, I always recommend keeping the outlier. I guess there are probably some extraordinary circumstances when you might not want to do that, but as a general rule, I'd say that's what you'd want to do. And then I would probably at this point decide to move on to a Friedman test. So next we're going to determine if there is normality. And we're going to look at the Shapiro-Wilk test for normality. Just like we've been doing all along, here are the sig values. I can see that they're all above 0.05, so it looks like we do have normality. Great. If we did not have normality, we remember those choices too. I think you can transform your dependent variable. You can use a non-parametric test like the Friedman, or you can carry on regardless. Again, I would say use that non-parametric test, use the Friedman if you violate normality. Okay. So now let's look at the procedure. Basically, it's breaking it down, telling you have a couple of choices here. You can do the one-way repeated measures ANOVA with a post hoc test. In other words, we're going to do it the same way we did the regular one-way ANOVA, and we're going to look at all the possible comparisons afterwards. And then if you had specific hypotheses, you can do contrast instead, some custom contrast. We're not going to get into that in this course, but they are there and they are discussed in Laird. So if that's something you need or want to discuss further, you know, you can look in Laird, you can talk to me, those sort of things. Okay. So let's look at the procedure. Now, this is one where, unfortunately, there is a split between how it works right between 24 and 25. And I know if you're using the school version, you're on 24. And if you bought your version, then you're on 26, I believe. You're not on 24, I suspect. So just pay attention to this part. And so again, if you bought it, I'm pretty confident you're on 26. And you can probably look at this first part here. Okay, so we start off by going under Analyze, General Linear Model, Repeated Measures. Now, the first thing we have to do is kind of name our within subjects factor name. So it has factor 1 at the top, and we're going to replace it with something more meaningful for our within subjects factor. So in this case, we use time because we were measuring things at pre, mid, and post. Had it been the phone situation, maybe we would have put in condition, or maybe we would have put in phone. Okay, doesn't really matter too much what you name it, although keep it relatively short, simple. Probably lowercase would be nice, you know, and don't go too elaborate. Okay. So here's time, how many levels? 3, because we had pre, mid, and post. Then we click the add button to bring that down. Okay, oops, sorry. Next, we're going to enter a measure name. Okay, this reflects the name of our dependent variable. Since our dependent variable is CRP, and that's C-reactive protein, we just entered CRP here. Had it been the the simulation, had it been the scores and the simulation of the driving simulation, maybe we would have typed in sim here or driving or what have you, wherever we were measuring. These don't matter very much except in terms of helping you keep track of things. But SPSS doesn't really care what you use. So we added that in as well. So now we have our time and we have our CRP. So now we click on the define button. Let me show that to you again. All right, at the bottom of this, there's the define button. So we click on that button. And we bring these, and once you hit the define button, excuse me, you'll be presented with this on the right side. The dash question mark dash 1 comma CRP and etc. for 2 and 3. This is a rather long explanation as to exactly what it's doing here. I don't think it's really all that critical. You are welcome to read through it to help your understanding. And we can always talk about it more in class. But basically, this is indicating level 1 of the within subjects factor, level 2 of the within subjects factor, and level 3 of the within subjects factor. So when you bring over, and you are going to bring over your CRP pre, mid, and post, just bring them over one at a time and make sure they match up. Okay. So as you can see here, we transfer the CRP pre, the CRP mid, and the CRP post into the question mark 1, question mark 2, question mark 3 CRP placeholders. Okay, so we just brought over from the left to the right. Okay. All right. Okay. Now we're going to click on, there's that again. Now we're going to click on the plots button, which is right here in that last screen. You see model, contrast, plots, the third one down. Okay, so you're going to click on that plots button and you'll be presented with the repeated measures profile plots dialog box. Bring time over to the horizontal axis. And then you click add. See if I can, yeah, I'll show you here. Bring time over to horizontal axis, press add. It'll add it to the plots. We will leave that as a line chart. And then we'll click on the continue button. And next we want to click on the EM means button. So I'm going to have to scroll back a little bit to show you. Yeah. Here we are back where you click the plots, go 2 more down and you'll click EM means. Okay. And this time you're going to bring over time. Sorry, it's a little bit awkward. This time you're going to bring over time. And then you can click on compare main effects. And it's going to give you an adjustment. So I'm just showing you again, estimated marginal mean to bring over time, display means for time. Click on compare main effects, and then you can select different adjustments. This one talks about the Shidduch adjustment and the Bonferroni adjustment. I think Bonferroni is standard and perfectly fine to go with for this class. There's nothing wrong with other ones necessarily. You know, like I said, the Shidduch is also a perfectly good one to use, but let's go ahead and use Bonferroni just for this class. click on continue, click on the options button, and this time you will click off descriptives and estimates of effect size. And then you click on the continue button and you click OK. So just to make sure you understood where the, I'm going to have to go one more time to show you where the options was. So, okay, so here on the last one was options. The last one was options. So when, like I said, you click on that, you click off these two things and you will be set to go. Click on continue, click OK. So let's briefly go through how this would look if you are using version 24 or somehow using something earlier. You still click on general linear model and repeated measures. You do the same business with time in 3. You do the same business with CRP. You bring it over. I mean, it gives you this, then you bring over the CRP pre, mid, and post. I'm skipping past all that. To get your plots, you bring over time to horizontal again. You click add, and it brings it down for you. Continue options, bring over time. Bring over time, click off the compare main effects and Bonferroni, continue, and OK. Oh, sorry. The difference is, one of the differences anyway, is that you, as opposed to clicking options, your descriptive and estimates or effect size are right there on the same page. So make sure you click that. Okay. All right. Now let's go on to interpretation of results. Okay. So one big thing we're going to look at is to whether sphericity was met or was violated. And we're going to do some different things depending on whether it was met or violated. Now, keep in mind, we're still going to stay with repeated measures ANOVA either way with this. It's just a matter of which results we're going to use to interpret. Okay. So we start off with some nice descriptive statistics. Yeah, just showing you what the within subjects factor is: CRP pre, CRP mid, CRP post. And then we get into our descriptive statistics here with our means and standard deviations. Okay. And ends, which should hopefully be the same across pre, mid, and post. We hope so anyway, right? Okay. So here are our means. We also were given our standard error and 95% confidence interval. And here's the plot we made. Interesting. Looks like something's going on here. We'll see if it's significant later. Okay. Next, we're going to test for the assumption of sphericity. And you will see an area that says Mauchly's test of sphericity. We're looking at this sig value right here. Okay, so this Mauchly's W, approximate chi-square, df, and sig. That's the sig value. We're looking as a comparison to 0.05. If it's less than 0.05, we have violated sphericity. So in this case, yes, we violated sphericity. Okay, all right. All right. Basically what this means is that later on, we're going to use one of these three things to interpret. Now, I recommend the Geyser greenhouse. Oh, excuse me, it really is between the Geyser greenhouse and the Heinfeld But I recommend the geyser greenhouse. I think that's, again, Heinfeld is slightly more conservative. It's fine. There's nothing wrong with it. But again, for consistency, let's go with the geyser greenhouse for now. Okay. So if the sphericity was good, if sphericity is assumed, this is our test of within subject. So it's a little bit different for what we're used to with our SSDF, mean square F and sig. And it's not too different, but it's different enough that it's worth talking about. So if sphericity is assumed, we're using these top lines for time and for error. Okay, all right. And I'm just going to scroll down to show you how it's actually taken apart. So if sphericity is assumed, then we would do F, this DF at the top 2, comma, this DF in the next group at the top 18 equals 26.938, comma, P less than 0.001. It even says for APA style, you would say 0.001. This is a different style that says 0.0005. We say 0.001. Okay. And this is a lovely effect size, partial eta squared, that we can use as well. Okay. And here again, it talks a little bit more about effect size, 0.750. All right. The way you write that effect size up is you can write it as either eta with a small p, with like a small p after it, or just partial eta squared equals 0.75. I'm partial to the partial rather than the NP because I just think it's a little bit easier to understand, but it's up to you. Okay. This is another way to get an effect size. This is another way to get an effect size. And K stands for number of different levels you had. So in this case, we had 3 levels. So 3 minus 1 is 2. F minus 1 takes the F value minus 1. And then we go K minus 1 again times F minus 1 again plus the N, how many participants we had, times again the number of groups. So you can see how that's worked through. It's perfectly fine to use this one. There is, it's not required. I think since eta is given to you, we've talked about the difference, I believe, before between these two. But since eta is given to you, why don't we just go ahead and use that one? Okay. But you know how this is calculated should you need it for a future purpose. Okay. All right. So again, we were talking about all this as sphericity is assumed. And then at the bottom, here's a little bit of a write-up if sphericity is assumed and you have no statistically significant result. But we'll get into reporting in a little bit, so I wouldn't worry too much about that. Okay. Now sphericity is violated, and I think this will happen more often than not, unfortunately. Then, like I said, we go with the geyser greenhouse. Same game, we're just using the second row across and the second row across in the second column, in the second section, sorry. Okay. So you can see we're still, now it's just that the numbers are a little bit weirder, but we're still pulling them from the same place. F of, now for the geyser greenhouse or greenhouse geyser. I've always called the geyser greenhouse. Either one's fine. F of 1.296, comma 11.663 equals 26.938. P less than 0.001. I know these look so similar and you're like, well, does it really even make a difference? It can, it depends on the situation. But yes, sometimes it can actually make a difference. Okay, and our effect size again is to 0.75, or you can calculate it as so. Okay. And this is again how one might write up a non-statistically significant result for this. Now let's look at the post hoc. So if you did have a statistically significant result, we might want to look at post hocs. In fact, I'm sure we would. And you can come down to the section of your output that says pairwise comparisons. Now this is very, very similar to the ANOVA pairwise comparisons. And you can see we're going to compare 1 to 2, 1 to 3, and then 2 to 3. 1 to 2 and 2 to 1, and it shows us this in the next section here. 1 to 2 and 2 to 1 are basically the same thing, they're just inverted. And it even does a nice job of showing you, well, I'll come back around to it. It shows you how really in the 95% confidence interval, the 0.242 gets moved to the right to negative 0.242. And the 0.538 gets moved to the left for negative 0.538. So just depending on if you want to live in the world of negatives or positives, or how you're comparing your variables, to be quite honest, how you might want to report that. But they're both there for you. Okay. Okay, so in terms of interpreting the results, here is the means again. So what I mean when I say it depends on the order of your results is if I was predicting that CRP pre would be higher than CRP mid, then it might be helpful to just use this top line of 1 minus 2 with the 0.390 and et cetera for the mean difference in the 95% confidence interval. If I was coming from a standpoint of saying that CRP mid will be less than CRP pre, rather than CRP pre more than CRP mid, then maybe I'd want to come at it from this angle right here, the 2 minus 1 rather than the 1 minus 2. It's obviously the same thing. It's just a matter of how you want to report it. Okay. Okay. And here's that point where I promised they show you how these are really just inverted. Okay. So they always do this backwards. From the way I think of it, they tell you to take the last two and then this third row. I always take the first two and then the fourth row. It doesn't matter which way you'd like to do it, as long as eventually you compare 1 and 2, 1 and 3, and 2 and 3. That's what you got to do. Okay. All right. Okay. And if that's confusing to you, I definitely recommend maybe reading through this a little more slowly and at your leisure, so that you can see how it actually compares the two. Okay. All right. So let's get into some reporting. Notice I skipped the simple contrast for 21 and 22, the simple and complex contrast, and we go straight into reporting. So I'm going to switch this over to APA, and basically this gives you some write-ups for not statistically significant but sphericity met, not statistically significant and sphericity violated, and not statistically significant sphericity violated and post hoc test. I guess they didn't give us statistically significant sphericity not violated with post hoc tests, but I think we can probably be okay with that one. We just would, use the line from up here with sphericity is met. Okay, so I'm not going to read all of these, but I will go through the last one, I think, with you, just to because I think that's the most complicated one, just to give you a sense for it. But we can talk through any of them again in class. So a one-way repeated ANOVA A one-way repeated measures ANOVA was conducted to determine whether there were statistically significant differences in CRP concentration over the course of a 6-month exercise intervention. There were no outliers, and the data was normally distributed as assessed by box plot and Shapiro-Wilk, respectively. Okay, so Shapiro-Wilk, p greater than 0.05, or we can report the actual p if we like. Actually, no, we won't. We would report p greater than 0.05 here because there's actually 3. So let's not get into all of that. Unless there's a violation, then I would report it specifically. Okay. The assumption of sphericity was violated as assessed by Mauchly's test of sphericity. Chi-squared 2 equals 6.27, comma, p equals 0.043. Therefore, a greenhouse geyser correction was applied, and they give the greenhouse geyser. That came right from where we were first looking at the, where we saw what we were going to choose, okay? And then the exercise intervention elicited statistically significant changes in CRP concentration over time. There's where we pulled out the greenhouse geyser from the results. And the partial eta squared, with CRP concentration decreasing from pre-intervention, mean and standard deviation, to 3 months mean and standard deviation, to 6 months mean and standard deviation. Post hoc analysis with a Bonferroni adjustment revealed the CRP concentration was statistically significantly decreased from pre-intervention to 3 months. And it gives the result here of the post hoc. From pre-intervention to post-intervention, again, mean and 95% CI and P for the post hoc, but not from 3 months to post-intervention. Okay. I think that's a very nice write-up. I don't think I would really change anything from this one. I think it pretty much covers all the bases here. Okay, so I think you can pretty much use that as a model. There was something else I was going to point out to you about this. Yes. What I was saying before about the Shapiro-Wilk test, if that had been violated, then you should actually report out how it had been violated, which groups violated it, and the actual p-values. Okay, but I think you're used to that. All right, and then finally, let's take a quick look how we would do a graph in here. Okay, so graphs, chart builder. Let me show you that one more time. Graphs, choose chart builder. You get this open screen like here. And you're going to go to, sorry, it's being a little persnickety on me. You're going to go down to line into choose from. Then you're going to choose that first line option on the left and just drag it into that main white area. Next, we're going to bring over CRP pre, CRP mid, and CRP post. Sorry. Into this y-axis, into this dependent variable. Okay. And then we'll be presented with the following create summary dialog box. Click on the OK button, and then you'll be presented with the following screen. And you can see it says CRP pre, CRP mid, and CRP post. And yeah, the preview, by the way, may not be how it looks in the end. It's just a preview. So you can kind of not worry about that too much. And then you can click on the display error bars in the element properties. So if you go over to the right, element properties, and you can click the display error bars, I assume you'd like the level to be 95% for the confidence interval. So we'll probably leave it like that. Then you can click the y-axis 1 in the element properties. And here you can actually control your, I just want to point out, you can control your min and max here. If you, if it's not starting in the place you want it to start, you can actually control that. So, sorry, let me go back. I want to show you something. Okay, under, you can change, you can use the dialog box, change the axis label using axis label, and then you can put in what you'd like there. So here we put in mean. Okay. Now we can uncheck the minimum, put in custom, and we say we want the minimum to be 0. Okay. Now we can click the x-axis line. We're going to leave the default option selected. However, we could change the order of the levels if we wanted to. And then when you click the OK, this is what appears. The pre, the mid, the post, and the mean. Okay. So had we not changed the minimum to 0, it probably would have started us at 2 or maybe even 3, and we wouldn't, you know, it's nicer to start with 0 so we can kind of see how that looks. Okay. Now, once again, we have version 24 or earlier. We'll just look at the parts that actually seem to be different. So far, everything's looking good. Yeah. So the difference here is that we have an element properties that pops up to the right side. Okay, before it was element properties that was already there as one of the choices, and now it's a little bit, looks a little bit different, as you can see. Okay. Go ahead and bring them over like we did before. The create summary, we're good. And then here we are a little bit different in terms of how this looks. Sorry. We're going to be presented with the following screen where the continuous variables have been entered into the y-axis. We can click off display error bars again. And then we click on the apply to confirm these changes. Then we can monkey around with the y-axis element properties and change the minimum to 0. Then we can go down to the x-axis. And if we wanted to, we could change the order of those categories. And then when we click OK, once again, it appears. Okay, so what we're going to do next is go back to the main slide set, talk just a little bit about the Friedman test, and then come over and look at that at Laird. Don't worry, it's not nearly as long, but if you're looking for a point for a break, this might be a good one. Okay, all right. Okay, and we're back here. And now let's talk about the Friedman test. The Friedman test is the non-parametric alternative to the one-way repeated measures ANOVA test and is used to determine whether there are any statistically significant differences between the distributions of 3 or more related groups. So all it is it's our alternative to repeated measures ANOVA. As we talked about before, the groups are related as they contain the same cases or participants in each group, and each group represents a repeated measurement on the same dependent variable. This test is mostly used if the assumption of normality is markedly violated or the dependent variable is measured on an ordinal scale. So let's talk a little bit about that. Also, if the box plot indicates you have major outliers, that's another time you would actually also use the Friedman. So if you remember, we talked about having a dependent variable that's measured at the continuous or ordinal level. We talked about an assumption before with the repeated measures ANOVA that it was measured at the interval or ratio level. Well, what if we have something measured at the ordinal level? Okay, so like continuous variables we talked about, time, intelligence on an IQ score, exam performance, weight, so forth. But let's talk about some examples of ordinal variables. Well, Likert items, 7-point scale ranging from strongly agree to strongly disagree. Now, by the way, some of you might be immediately thinking, but I have Likert items. Well, you might very well, but if you're adding them together, that gives you more variability. So we're just talking like if your final score was rated on a 7-point scale, you might want to really think about this, Friedman, okay? Physical activity level, if you had 4 groups, sedentary, low, moderate, and high. Customers liking a product ranging from not very much to it is okay to yes a lot. Pain felt by patients after hip replacement surgery, no pain, mild pain, moderate pain, strong pain, and severe pain. Amongst many other ways of ranking categories. Okay. So anything that you think of as sort of more of a rank order thing is most likely ordinal and most likely should be considered for the Friedman. Okay. Assumption 2, you have one independent variable that consists of 3 or more categorical related or matched cases. Okay, well, that's what we had for the repeated measures ANOVA, so that makes sense. Okay, so now we hop on over to Laird once more. This time we're only going to go through these 7 pages, so it won't take nearly as long. Okay. Okay, and we're back. We're back with the Friedman test on page 5. We're going to go from pages 5 through 11 here. We have basically the same setup as we did before, okay, with the CRP, C-reactive protein, and our exercise. So that's what we're looking at. Okay. Here's our variable view. Here's our data view. Okay. So let's assume we either violated the outlier assumption or the normality assumption. Here's how we're going to run a Friedman test. We go analyze non-parametric tests, related samples. Under objective, we can leave the automatically. Under fields, we're going to bring over our CRP pre, our CRP mid, and our CRP post. And then you can just hit run to generate the output. You could go under settings, as we've talked about in the past, and choose the Friedman, just to be sure that that's what runs. Now, again, this is going to talk about generating median statistics, and I will go through it with you. But if you've already run the Explorer, you probably already have median statistics. But sometimes it's easier to just produce them like this, so let's talk about it. Analyze, compare means. Bring over CRP pre, CRP mid, CRP post. And under options, we can get rid of the mean and the standard deviation and bring over the median. We can leave a number of cases or we can ditch that too. It's up to you. Click continue and click OK, and that will give us our medians. Okay, ready to interpret results. So we'll go through and talk about different pieces and how we're actually going to look at this, okay? So here we are. We got a result. It says reject the null hypothesis. And in our model viewer, we can see how this looks. 10 cases, our test statistic, our degrees of freedom, and our asymptotic p-value. I'll switch this over to APA just so you can see how this little piece would be reported with a chi-square. You can see the 17.864, and again, it would be p less than 0.001. Okay. And here's the median values that it gives you right here. Okay. So if we had a significant result, if p is less than 0.05, we might want to look at some pairwise comparisons. So let's do that. Okay. So the way you get this, let me just kind of scroll down here, is once you have your model viewer open, you go to the bottom on the right side and you choose pairwise comparisons. Okay, had related samples test view, you're changing it to pairwise comparisons. This will present the pairwise comparisons window with the graph. And usually orange denotes a significant difference. So we think that probably between midway, between pre and midway, we have a difference. Between pre and post, we have a difference, but probably not between midway and post. And here's how it actually gives us our results. A little bit easier to read than the repeated measures. Post to pre, that's significant. Midway to pre to midway, that's significant, but midway to post is not significant. Okay. And then let's look at some reporting. I'll switch it over to APA. Let's look at this top one because that's the statistically significant Friedman test with pairwise comparisons. A Friedman test was run to determine if there were differences in CRP concentration during a 6-month exercise program. Pairwise comparisons were performed with a Bonferroni correction for multiple comparisons. CRP concentration was statistically significantly different at different time points during the exercise intervention. Chi-square, DF, goes into parentheses, equals 17.684, comma, P less than 0.001. Post-hoc analyses revealed a statistically significant difference in CRP concentration from pre-median to post-median, P less than 0.001, and from midway median, P equals 0.002, to pre-intervention, but not post-intervention and midway. Probably would have just phrased this slightly differently. From pre to post I like, but then I would have said, and from pre to midway, probably, and just phrased it that way. Okay. I see they're trying to get it all in one, but I don't know, it kind of looks a little awkward maybe. Maybe from pre to midway and post, I don't know, just sounds a little awkward to my ear, but the basic idea is here. Okay. So that is it pretty much for the Friedman. Okay, so now we're back to our slideshow. We went through the Friedman, we went through the repeated measures ANOVA, and if you have been keeping up with that little table we've been creating, you can see how very similar the repeated measures ANOVA is to the t-test for dependent samples. Before we had 2 values per participant, now we have 3 or more. In every other respect, those 2 columns are the same. Okay. All right. So next we're going to move on to the factorial ANOVA. We'll spend a little bit of time talking about what that looks like, and then we'll move on to the remaining types of ANOVA just to get a handle on what they would say. So I'm going to actually break the recording now. So there will be a part 1 and part 2 of this. And I invite you to come back once you've digested this and listen to part 2. It will be, I think, a bit shorter than part 1. Okay. So see you in the next recording.